All right, so we're just going to dive straight into it. First off, there's my presentation, so I'm going to try to give an overview of these topics around embodied carbon of HFC blowing agents and insulation. So first off, what is embodied carbon? When we're talking about embodied carbon, we're referring to the environmental impacts of construction materials used in your building. So all the concrete, steel, wood, glass, and insulation, we're looking at those emissions associated with those materials, from extracting those resources like mining or processing those materials, manufacturing, transportation, use, and then also towards the end of life. How do those materials get handled at the end of life? Does it get landfilled? Does it get recycled? We're looking at emissions throughout, from the cradle to the grave of these materials. And so many of you may have seen this pie chart before. This is looking at the global annual CO2 emissions. So every year, operating all the buildings on the planet each year takes up about 28% or makes up 28% of global CO2 emissions. Now, a further 11% is associated with the embodied carbon of constructing all the new buildings that are taking place each year. Now, that 11% slice of the pie has been mainly associated with the key core and shell materials, so the structure and the envelope materials, so like concrete, steel, and whatnot. But there's some recent estimates that are kind of looking at what about the other building materials in there as well. So some estimates show maybe it makes up another about 10%. A lot of these emission figures is like, it's a bit challenging to figure out how you slice it up in the right way sometimes. But let's say it's at least 11% of global CO2 emissions is embodied carbon. Now, I want to zoom out a little bit to get a high-level perspective of why all of this stuff matters. When the IPCC came out with their climate change report on limiting global warming to 1.5 degrees Celsius, here's some perspective on what it actually takes to hit these climate targets. So if we were to hit our 1.5 degree scenario target, that means this year, 2020, we need to peak global CO2 emissions. By 2030, we need to half it. And then by 2050, we need to get to zero, and then we need to go negative. So that's the scale of how significant these emission cuts are. And to put it more on practical annual terms, to hit the 1.5 degree scenario target, that means every year we need to reduce global emissions by 7.6% per year. If we went for the less stringent 2 degree target, that's 2.7%. And many of you may be wondering, given the pandemic and us stopping all the planes and like all the stuff in the world, what's the emissions impact of that? And so the latest estimates that I've seen on that front is from the International Energy Agency. This was in late April. Their projections for this year is 8% reduction in global CO2 emissions. And so think about how drastic these emission cuts are already happening by basically stopping big sectors of the economy. That's getting us 8% for this year. So it gives you a sense of what the task is at hand. Now, another thing to think through is that these scenario targets oftentimes don't include tipping points or positive feedback loops. And so if we set into motion some of these larger natural forces like the melting of the ice sheets or pausing the ocean circulation currents and whatnot, all of these can have positive feedback loops, which make it even harder to stabilize the climate, which means it's really important to look at when those emissions reductions take place. And that's part of why there's been a lot more focus around embodied carbon lately, is because these emissions are like happening upfront, they're happening early, and they have a big impact on our whether or not we hit these climate tipping points in the immediate term. So it matters when these emissions take place. And to give you some perspective, this is not just a hypothetical thing. In British Columbia, in our wildfires in 2017 and 2018, that was equivalent to 3 times all of BC's total annual emissions. And same thing with Australia. Last year with the wildfires that were taking place in Australia, projections were that would release 900 megatons of CO2. So that's equivalent to double all of Australia's emissions. And so we really need to be cognizant of like not tripping over these tipping points. Now, if we look at what the global CO2 or greenhouse gas emissions are, it's important to recognize that it's not just all CO2. There's also methane, nitrogen dioxide, there's these fluorinated gases, which is these F gases. And so this is what we're talking about today, is when we're referring to HFCs, hydrofluorocarbons, it's basically a whole series of different fluorinated gases. And so it makes up this slice of the overall emissions. And these are in CO2 equivalents. This is important because even though that seemed like a very small slice compared to everything else, fluorinated gases are actually the fastest growing source of greenhouse gas emissions. So if you actually look, comparing that to just overall GHG emissions, CH4, which is methane or nitrogen dioxide, fluorinated gases are increasing at a rate of about 4 to 6% per year. This was the average over over the past decade, basically. And so this is split between OECD countries and non-OECD countries. So across the world, this is actually one of the fastest growing sources. And so if you actually play this out in the future scenarios, what they're saying is that without fast targeting policies to limit HFCs, it can increase 30-fold by 2050. And so that is so significant that it could, by itself, raise global warming by 0.1 degrees Celsius by 2050 and increase 5-fold to 0.5 degrees Celsius by 2100. And so that's why when the Kigali Agreement came in, there's been a big global effort to limit these and regulate these emissions. It's because these are some of the most significant and potent gases from a climate change perspective. Now, if we actually look at the fraction of greenhouse gases that stay in the atmosphere over time, this is something that people may not fully appreciate. So when we're looking at calculating embodied carbon, when we're doing a life cycle assessment, the environmental impact category that we're looking at is called GWP, global warming potential. But there's actually a time horizon perspective that we look at it. And so almost every emission statistic calculation that you look at, it's referring to GWP 100. And that's because for different greenhouse gases, they stay in the atmosphere for different lengths of time. So for instance, methane can stay in the atmosphere for something like 14 years. And so it decreases significantly in terms of its impact on radiative forces. Whereas CO2 emissions, after even a few hundred years, there's still like 30% of it in the atmosphere. And so when we're looking at GWP 20, for example, for methane, you may have heard it's 84, or sorry, actually the number that you probably heard is GWP 100 is 28 times worse than CO2. So for each unit of methane, it's 28 times worse from a climate change perspective than CO2. But if you look at a 20-year time horizon, it's 84. And so this is true not just of methane, but also for refrigerants. So HFCs, which are basically like these refrigerants. So when you say CR134A, that's the same as HFC 134A. You can see that the 20-year time horizon for these figures is about 2 to 3 times higher. And these are not the typical figures that you'll see. It's important to note that the atmospheric lifetime for most of these HFCs are under 20 years. So you can see, for instance, R134A, the atmospheric lifetime is 14 years. So some may argue that it's also useful to look at the GWP 20 numbers in addition to the 100 numbers. That's not to say that this is like an accounting error or something. There's a reason why we do look at the 100-year time horizon, and it makes sense because there's many different gases, some of which last much longer than 100 years, some of which don't last as long. And so, but it's just something to keep in mind. So for example, these are the characterization factors. It's using, this is one of the LCA methodologies. So in North America, we use what's called Tracy, but in Europe, they use CML. And I'm showing CML in particular because they actually show GWP 20 factors. So you can see these are all these different greenhouse gases, and they're ranked from highest to lowest. So, the highest is sulfur hexafluoride. It's like 23,000 times worse than CO2. And you can look at the difference between GWP 100 versus 20. And you can see for many of these gases, what's the GWP 20 versus GWP 100. So for these green section ones, that means these ones actually, the GWP 20 numbers are lower than the GWP 100. However, all these red ones show that the GWP 20 is higher. And so what I showed you earlier, the R134A, that's this line right here. It's pretty small, I know. It's, it's like 200 something percent if you look at the GWP 20 compared to the 100. And that also means that if we limit these emissions, we can actually have a very quick impact on the climate, because these are short pulses of emissions that can quickly decay through the atmosphere and reduce. That means when we stop emitting them, there's less kind of momentum. So this is a visualization of what happens, for instance, like in year 2005, we have a pulse of emissions. It decays over these years. But then the next year you have another pulse of emissions. So you can see how this all adds up. But then, let's say at 2030, we stop emitting these gases very quickly. The global warming, the radiative forcing limits. And so the reason why I kind of got turned on to this topic was this book called Drawdown, which is a big comprehensive research effort to look at what are the top solutions to global warming. And what's surprising is that while most of us think of things like solar or wind, the number one solution that they illustrated in their book was refrigerant management. And what they're trying to look at is between 2020 to 2050, so over the next 3 decades, what has the greatest potential for greenhouse gas reductions. And so what they're showing here is 89 gigatons of CO2 removed. So that's equivalent to something like 2 years or so of global emissions just from refrigerants, phasing this down. So it is a very significant thing. And in the embodied carbon world, we talk a lot about concrete. Concrete comes in at number 36 in the list. So it's the mitigation potential that they're showing there is around 7. And so, it drives home the point that we really need to look at refrigerants, which are in our mechanical systems, but it's also in our insulation. Now, when we're looking at embodied carbon, comparing embodied versus operational, this is the typical lifespan of a building. So over 60-year lifespan, you have the yellow emissions, that's the operational carbon emissions, heating and cooling the building. But in the embodied carbon side, that's all the red emissions. There's a big pulse of emissions that happen up front when you build the building, and then a little bit during the maintenance and replacements, and then a bit at the end of life as well. So we have these formalized life cycle stages. So the thing to note is module A is all the materials that are upfront. It's before the building is in operation. Module B is the use phase, the operation of the building. So that includes things like replacements and refurbishments. And in our case, in this topic, looking at the use phase, the off-gassing of the blowing agents, that becomes more significant here. And then module C, which is the end of life phase. So looking at the waste and disposal. I'm just going to skip over some of these slides, actually. So now embodied carbon, let's look. I want to give you some sense of the scale of these emissions. So this was a study done by Athena that looked at 10 multi-unit residential buildings. The average across those 10 buildings was 318 kilograms of CO2 per meter squared of floor area. And on the operational side, with the City of Vancouver's rezoning requirement, the operational GHGI is between 5 to 6 for residential buildings. So each year to operate the building, between 5 to 6. Embodied upfront, that's like 318. Now, granted, on the operational piece, those are really low numbers. That's reflective of near passive house level performance and fuel switching to electrification, and we have a fairly clean electricity supply, mostly hydro in BC. So that's how you get these really low numbers. And obviously these can vary significantly. A baseline building that wasn't particularly high performing, maybe closer to 20 kilograms of CO2 per meter squared in terms of operation each year. Whereas a city like Calgary, which has different climate, higher carbon electricity intensity, and also they use natural gas for heating, it can be as high as 71 each year, right? So that's on the operational piece. Know that these emissions can vary significantly. But same thing with embodied, right? So this was a study that was done by the Carbon Leadership Forum. They looked at over 1,000 LCAs from around the world. And you can see the ranges of these emissions by different building types. Many of them fall in the 200 to, let's call it 600 range. And they can go as high as 1,000 kilograms of CO2 per meter squared. So this is a whole building basis. And so there's different scales at which we can look at these LCA studies. We have the whole building level. You can look at the assembly level, so looking at just a wall assembly. You can look at individual products or individual materials, and that's where EPDs or environmental product declarations come from. And those are calculated using life cycle inventory database, so sort of a background database that they draw from. And so if you're not familiar with environmental product declaration, it's sort of like a food nutrition label for building products, but instead of looking at health impacts, we're looking at the environmental impacts. So we look at not just the embodied carbon, which is called global warming potential, but we also look at things like ozone depletion, acidification, eutrophication, smog formation. These are third-party verified LCAs, basically, of the manufacturer. So they can say per unit of my product, what's the emissions associated with it. It avoids greenwashing, and these EPDs can also happen at the industry average level and also on a manufacturer-specific basis. And so you may have heard of this EC3 tool, which is an open source database of all these EPDs. So you can actually look in here to find different manufacturers or also the industry average EPDs for different insulation types, different concrete types, and this is all free to use. And so I highly encourage you guys to join this. It's at buildingtransparency.org. You can sign up there. So now we're going to get into the meat of this point. What I've noticed is that in looking at the EPDs, for XPS and for spray foam, I've noticed that the emissions in the module B and the module C stages are actually quite significant. And so my understanding is that this is mostly attributed to the blowing agents. So the HFC blowing agents that are used in both XPS and spray foam are quite high. And most EPDs that you see, oftentimes they're mainly focused on the A1 to A3 phase. So that's accounting for the resource extraction, transportation to the manufacturing facility, and then the actual manufacturing and processing. That's A1 to A3. For the vast majority of materials, that is where most of the emissions are. However, in this particular instance, it seems like the off-gassing of the HFCs during Module B and then Module C at end of life are actually more significant than the A1 to A3 emission impacts. And so you can actually see this illustrated. I basically pulled out these values from those EPDs. And because I can't find an industry average XPS EPD, I looked particularly at Dow and Owens Corning, which were the main XPS EPDs that I could find out there. And you can see, the A1 to A3 are still fairly significant, but actually the B1 and the C stages are quite high. So they make up a huge percentage of the total emissions from module A to C. And you can see, for instance, the ones that I've highlighted in red, these are HFOs. So this is what the industry is trying to transition towards. These are lower global warming potential agents. So HFCs are much higher global warming potential. HFOs are typically lower. And so in this instance, this is one XPS manufacturer in Germany. And so you can see their module B is like nothing. And they use they use HFOs for that. So the overall emissions are much lower. Same thing with the spray foam industry. These are the spray foam industry's industry average EPD. And what's interesting is they actually published an EPD for HFC and one for HFO. So you can actually see the difference between HFC versus HFO. And so in this next slide, I've included all those figures that you saw earlier, but instead of breaking it down by life cycle stage, I'm looking at the total A to C impacts. And I put it in, normalize it to R values. So you can see, typically with an insulation providers, they report this per meter squared of RSI equal to 1, which is equivalent to R value of 5.68. So then I kind of do a translation between that to the R value. So now you can see by R value how these compare from R5 to R60. So for example, for XPS, typically it's R5 per inch. So R5 is like 1 inch, R60 is 12 inches of XPS. And what you can see is that these numbers are very significant. When you get to R60, 12 inches of XPS, that could be equivalent to 1,000 kilograms of CO2 per meter squared of whatever your envelope area or your floor area is. And so this can get to the point where it's actually on the scale of entire whole buildings. And so this was what I've spent some time kind of investigating this, and I was very surprised because I couldn't see these numbers reflected in our whole building LCA results, which typically show you that most of the whole building LCA results are between 200 to 600. At the outer edges, it might be 1,000. But to see the insulation itself like this high, I hadn't seen it reflected in both Athena before. And so I reached out to Athena and also to Tally and also to One Click LCA. And what my sense is that all three of those providers, in terms of the standard XPS values that they have in there, they're about 10 times lower than what I'm seeing from the Owens Corning and the Dow EPDs. And this is my understanding of this from their explanation, is that this may be due to use of old XPS data that's from Europe. And in Europe, I believe they have regulation where they've already banned a lot of the HFCs. And so those numbers are significantly lower. And so that could be one of the aspects, or it could be how we're handling the HFC blowing agents in Module B and Module C, and what are the assumptions there. Because many of the EPD providers, when they provide this, they don't actually, most EPDs report A1 to A3 figures, but they don't always report module B or module C emission figures. And so that may be one of the complexities there, is like, how do you kind of deal with all of this stuff? Anyways, I think all three software providers are aware of this, and so they're looking to address it soon and update their databases. But I think it's important for the whole design community to understand that, like, I think for a lot of our whole building LCA studies, if we have a lot of insulation, XPS or spray foam in there, it could have been underestimated in terms of those emissions. And what I want to emphasize is that this is not actually to like make anybody look bad or per se, right? Like, I think in this field of embodied carbon, there's actually a lot of blind spots in the industry. And there's also, I mean, the people that are behind these softwares, that like, they actually have been the pioneers and the leaders, especially when nobody's really looked at these figures and these statistics, and you know, nobody paid too much attention to it until now. And so I think what's valuable now is that because we're paying more attention to these figures and we're looking at do these numbers make sense or whatnot, we as an industry can kind of improve from there. So as an example, just a quick note, these red ones that I've highlighted, these are HFO based insulation figures. So you can see, at least from the spray foam, and also comparing, for instance, the German XPS, which uses HFO, versus these other XPS, it can be about a fifth of the impact. Now, in North America, I don't think there's been any EPDs released by Owens Corning or Dow or wherever else with the new generation. So I'm not sure what these figures will show up to be, but at least just going from this, like, it should be a quite significant drop in emissions overall. And so I think I want to end on this point, is that actually I heard this from Martin from Austin. He was quoting somebody, but he was saying, you know, when we're thinking about problems, the problems that are worth solving are the ones that are really big, like they have a big impact in the world. They're solvable, so there's something that we can actually tackle with, there's some tangible thing that we can do about it, and also that they're ignored, like there's not a lot of attention paid on it. Those are the things that can have a huge impact. And so when I look at embodied carbon, which by itself I've oftentimes referred to as a blind spot in the industry, in that we've neglected it, we've focused so much on operational, but completely neglected the embodied piece. Similarly, within the embodied carbon, there are things that we need to look at that are potentially blind spots, like our insulation, our refrigerants, what's the rate of leakages in our VRF systems, for example. What about the actual materials used to make up our mechanical, electrical, and plumbing systems? What about the interiors and how quickly those get changed out with each tenant improvement, for example? What about the forestry-related impacts on the land use changes? And even looking beyond just material substitutions, what about the growth in floor area? There's a recent article that was posted in the CLF online community talking about this. Like, maybe we should be looking not on a per meter squared impact metric, but looking at it per occupant, for example. So these are just some of the things that I think, as we all get into this and learn more about it, and I'm definitely learning a lot about this myself, we'll discover that there are blind spots, and they create a lot of opportunities for significant emissions reduction. And so so this is the conclusion of my presentation. I'm very passionate about embodied carbon. If you guys want to partner on case studies or want to look at some specific topics, feel free to reach out, or if you have any questions around this. With that, I'll hand it over to, with that, actually, I want to take a few questions. I know I haven't been doing so good on time, so I'll try to, we'll just take maybe one or two questions, and then if there's more time later, we can tackle it. So Lorena, is there any? Yeah,
so there's only a few questions. One from Hayomeyer. Sorry if I mispronounced your name. How do the numbers for, if you can please unmute yourself, or I can unmute you too.
Yeah, I am unmuted myself, but actually
Perfect.
Somebody, Jamie, pointed out that it was at the bottom of the slide, so I think the
question
was answered, but I was wondering, how the emissions
right
to other materials.
Yeah, that was this one. So these are some of the other ones. Like there's EPS, GPS, polyiso, mineral wool, cellulose. So you'll see these other categories.
Yeah, thank you.